Physics is the language the universe uses to describe itself. It is not an opinion, not a human convention we could have chosen differently. It is the set of rules that governs every collision, every orbit, every particle that has ever existed. It works in the cold, silent vacuum of space. It works inside the cores of stars at 40 million degrees. It works within particle accelerators where collisions occur on scales the human mind cannot visualize. It works everywhere, except in one place. At the center of a black hole, the equations that describe the universe produce a specific result, infinity. And infinity, in physics, is not an answer. It is a signal of breakdown, the calculator being thrown onto the table and refusing to continue. To understand why this happens, you need to understand what a black hole really is, not the simplified version, but the unsettling one. Start with gravity. Most people learn that gravity is a force. Earth pulls you, the sun pulls Earth. Everything pulls everything with an intensity proportional to mass and inversely proportional to distance. That description works for most practical purposes, but it is not what is truly happening. What is happening is that mass bends spacetime, the four-dimensional structure that composes reality, and that curvature is what we call gravity. An object is not pulled toward the sun, it follows the straightest possible path through a space that is curved around the sun, like an airplane flying straight while tracing Earth's curvature. Now imagine increasing that curvature. Compress more and more mass into a smaller and smaller volume. The curvature grows. At a certain point, and that point is exact and calculable, it becomes so extreme that even light cannot follow a path leading outward. Every possible trajectory curves back inward. This is the event horizon, not a surface, not a wall, but the boundary beyond which space-time geometry offers no escape. And at the center of this system, the curvature does not stop increasing. A star with 20, 30, 40 times the mass of the sun spends most of its life in brutal equilibrium. Nuclear fusion in its core produces enough pressure to resist gravitational collapse. When the fuel runs out, that balance disappears in fractions of a second. The core falls in on itself at speeds approaching a quarter of the speed of light. All that mass, potentially dozens of solar masses, is compressed into an ever smaller volume. Density rises unchecked, and physics, which followed all this with mathematical elegance, begins to stutter. At some point in this collapse, a singularity forms. The name is technical, but the implication is unsettling. A point of zero dimension with infinite density. All the mass of the star concentrated into something that has no size at all. Not something very small, something without size. The equations of general relativity, our best description of space-time behavior on large scales, reach this point and return infinity. Infinite curvature, infinite density. And infinity is not a place, it is where the map ends. What makes this disturbing is not infinity itself, but that general relativity is extraordinarily precise everywhere else. It predicted gravitational waves decades before detection. It explained Mercury's orbital precession when no other theory could. It described light bending around the sun with accuracy confirmed since 1919. It works, and yet, applied to a black hole's interior, it produces a result it cannot interpret. This is not a minor technical detail. It is a hole at the heart of modern physics. There exists a second theory describing the universe with equal precision but on entirely different scales. Quantum mechanics. It governs subatomic particles, energy fields, and the smallest structures of the vacuum. It also works with unsettling accuracy. And when forced to describe the center of a black hole, it breaks as well. The two best descriptions of reality humanity has ever produced become incompatible precisely where they are most needed together. The singularity is not just the center of a black hole, it is the center of physics' deepest problem. Suppose you are falling toward a supermassive black hole, one residing at a galactic center containing billions of suns. We choose this deliberately. In a smaller black hole you would be destroyed long before reaching the horizon. Here, for a time, you survive long enough to observe. The first strange thing happens with light. Gravity bends not only matter but photons. Near enough to a black hole, photons can orbit in circles. In the photon sphere, gravity is exactly strong enough for this. If you hovered there and looked correctly, you could see the back of your own head, not in a mirror, but because light traveled around the black hole to reach your eyes. Curved spacetime turned into optics. But you are falling. As you descend, the universe behind you behaves strangely. Incoming light becomes increasingly blue-shifted as you accelerate toward the gravitational source. The universe compresses into a shrinking halo above you while darkness grows below. Not gentle darkness, but absolute absence, where no information arrives because none can escape. Now comes the dual perspective. To a distant observer, you never cross the event horizon. Gravitational time dilation slows your clock. You appear to freeze, redden, fade, lingering forever at the boundary. From your perspective, you cross without drama, no wall, no signal. The horizon is geometric, like crossing an imaginary line of longitude, except irreversible. Inside, direction toward, the center becomes a direction in time. Outside, you can choose spatial motion but not move backward in time. Inside, you cannot choose not to move. Toward the singularity, it lies in your future as inevitably as tomorrow lies in yours now. Resistance is meaningless. Acceleration hastens arrival. Passive falling maximizes survival. Perhaps hours in a supermassive case. Hours to contemplate what lies ahead. All accumulated mass converges there. Collapsed stars, gas clouds, perhaps entire systems. Yet the black hole retains no memory. From outside, 3 numbers define it. Mass, spin, charge, nothing more. A neutron star, a cloud, or a civilization. Indistinguishable, or are they? Here physics stops agreeing with itself. Quantum mechanics insists information cannot be destroyed. Burn a book, and every detail persists encoded in scattered particles and radiation. A black hole appears to violate this, reducing everything to 3 numbers. In the 1970s, Stephen Hawking showed black holes should emit radiation via quantum effects near the horizon. Virtual particle pairs form, one escapes, one falls in. The black hole loses mass. Over immense timescales, it evaporates. A solar mass black hole would last around 10 years, vastly longer than the universe's age. But Hawking radiation appears thermal, random, carrying no information. When evaporation completes, where did the information go? This is the information paradox. Proposals exist. Entanglement encoding information in radiation. Energetic firewalls at horizons. None are proven. We remain in theoretical territory beyond experimental reach. Most physicists suspect singularities signal incomplete theory that a quantum theory of gravity would replace infinities with finite extremes. Candidates exist. None confirmed. What we know is this. At a black hole's center, our 2 best descriptions of reality collide and disagree fundamentally. And in the far future, after stars fade and galaxies disperse, the last black holes will slowly evaporate over unimaginable timescales. One by one they will vanish, and with them, perhaps, the last traces of what fell inside. Unless we understand first